Good afternoon, everybody. Welcome on board for this last part of the webinar 2. We start by session 4. Session 4 is what about miscellaneous subjects, exotic subjects, gravitation control, and so on. We will see that. This is with Edoardo Russo as chairman of this session. And after, we will move to the last roundtable about the experience of pilots and controllers with UAP encounter. And we will have a very good team to share views and their experience. I don't say more. We will say that in time. Edoardo, if you wish, you can start now session 4.
Thank you. Welcome, everybody. This is the last session. It is a miscellaneous one, as Luc Denis was telling us. We will have only 3 papers in the afternoon, but they are very hard ones, heavy ones about very technical issues, electromagnetism, gravitation, propulsion, and technology. And last but not least, something more intrinsically about the UAP reports. We will have some very illustrious speakers. The first one being Pierre Marx, who is a former director at the National Space Center in France, of very long experience and competence, and he is also a member of the Sigma 2 Technical Commission. He will talk about the electromagnetism and gravitation. So please, Pierre, you can start.
Bien, alors je vais présenter ici une théorie de mon cru concernant la gravitation qui peut être créée par un champ électromagnétique. C'est un sujet pas très connu, mais qui mérite d'être étudié. Mélange suivante, s'il vous plaît. Alors, l'intérêt de cette théorie, s'il est correct, c'est que on peut démontrer que l'espace qui entoure ce qu'on appelle une bosse de champ est antigravitationnel. On le verra presque à la fin de ma présentation. Alors, ça pourrait être évidemment très, très important comme conséquence. Alors, ce n'est pas une théorie quantique, mais bon, ça ne la met pas en cause. Ensuite, c'est un petit peu difficile parce que l'électromagnétisme est une théorie qui a été n'est plus une théorie qui résonne, qui permet d'interpréter les phénomènes au niveau des particules. C'est-à-dire que c'est pas une théorie quantique. Alors, il faut savoir quand même que la gravitation fait l'objet de beaucoup de recherches au niveau justement de l'infiniment petit, des particules, et notamment il existe actuellement 2 théories qui n'ont pas fait vraiment leurs preuves, mais qui dominent le domaine. C'est la théorie des cordes, la string theory, et la théorie des gravitations en boucle, qu'on appelle le quantum gravitation. Alors, je vais faire ma présentation en 2 parties, qui correspondent à 2 articles que j'ai publiés dans une revue scientifique française, qui sont les Annales de la Fondation Louis de Broglie. Je dis simplement, Louis de Broglie a été un grand savant du XXe siècle, qui a joué un rôle très important dans la mécanique quantique. Et à la fin de sa vie, il a créé une fondation à son nom, qui dépend d'ailleurs de l'Académie des sciences. Et cette fondation publie un journal régulier avec ce qu'il appelle les Annales. Et j'ai été publié dedans en 2009. Alors, le point de départ de tout ça, c'est que actuellement, ces équations de Maxwell qui régissent le champ électromagnétique sont des équations différentielles linéaires. Alors qu'en fait, aucun phénomène physique n'est linéaire, quelle que soit l'amplitude du phénomène. On peut linéariser, mais pas considérer que c'est valable dans tous les domaines. Alors, en fait, le problème, c'est que elles n'ont jamais été mises en défaut. Même avec des champs très élevés qu'on s'est produits aujourd'hui, elles n'ont jamais été mises en défaut. Et en fait, ces équations ne tiennent pas compte d'une propriété fondamentale de la relativité générale d'Einstein, c'est que toutes les formes d'énergie créent de la gravitation, et notamment l'énergie électromagnétique. Donc, c'est une espèce de contradiction entre le fait qu'on a des équations linéaires qui ne tiennent pas compte justement de ça, alors que la gravitation d'Einstein, elle dit le contraire. Bon, je passe sur la manière d'y parvenir. J'ai donc utilisé le même formalisme que ce qui donne lieu aux équations de Maxwell, mais en supposant qu'on tienne compte de la gravitation que crée le champ électromagnétique, même s'il doit être très élevé. Parce que l'hypothèse, c'est en fait que les champs sont tellement élevés, que les champs classiques sont tellement faibles au niveau de la gravitation qu'on n'en tient pas compte. C'est la raison pour laquelle, probablement, les équations sont linéaires. Donc, je propose là deux axiomes, si je puis dire. Un potentiel extrêmement élevé de champ magnétique crée un champ gravitationnel mesurable. Et le potentiel électromagnétique, bon, je passe là-dessus parce que c'est un petit peu, il faut rentrer un petit peu dans la théorie, c'est une quantité vraiment réelle, et pour ces values très élevées, elle ne joue plus le rôle des théories de Jones. Enfin bon, ça c'est de la physique de base. Alors les équations de Maxwell, alors, elles sont divisées en deux groupes. Ceux qui savent ce que c'est, il s'agit donc du deuxième groupe. Le premier groupe n'est pas mis en cause. Ce sont des équations qui sont obtenues en variant, ce sont des équations de Lagrange qui sont obtenues en variant les composantes du champ électromagnétique, c'est-à-dire ce qu'on appelle dans un langage savant le tenseur de Faraday. Le second membre de ces équations, dans le vide, et quand il n'y a pas sans présence des charges, le second membre de cette équation est nul. Mais si on fait varier les composantes du potentiel électromagnétique, ce qu'on ne fait pas d'habitude, il apparaît un second membre qui est comme si c'était comme s'il y avait les charges présentes. Ce second membre est proportionnel à la fois à la densité d'énergie du champ et aux dérivés des composantes du tenseur métrique, le tenseur métrique représente la gravitation, vis-à-vis des composants du cadre potentiel. Bon, je passe, c'est quand même un peu compliqué à expliquer parce qu'il faut avoir fait un peu de relativité générale et on travaille dans un espace à 4 dimensions, c'est pour ça que vous voyez souvent le chiffre 4 devant une quantité physique, comme le potentiel. Donc, par analogie avec la 4 densité de courant, qui normalement se trouve dans les équations de Maxwell en présence de charge, on a appelé provisoirement, vous allez voir, la 4 densité de courant électrogravitationnel. Alors ça, c'est la deuxième partie de mon exposé qui a donné lieu à un deuxième article un peu plus tard, puisque c'est publié en 2020, pas très vieux, et qui est une application en réalité du premier. Le premier est une théorie un peu générale. Là, on va l'appliquer dans un cas très particulier qui est facile. Les calculs sont plus faciles, même si c'est un peu théorique. Alors, on va se référer un petit peu à ce qu'ont raconté quelques anciens physiciens célèbres du XXe siècle, des débuts du XXe siècle. Alors, entre autres, Lorentz, qui a été un des grands, c'est même fin du 19e d'ailleurs, qui a imaginé que l'électron, on va se centrer un peu sur l'électron, était un petit paquet d'énergie électromagnétique, uniquement d'énergie électromagnétique, qui est d'ailleurs pas faux, hein, actuellement c'est la vision qu'on a de l'électron. Ensuite, il y a eu en début du siècle, en 1812, et surtout avec Born et Linfeld en 1934, ils ont proposé un concept de champ qui est un champ qui n'est pas linéaire, justement. Les équations ne sont pas linéaires. Donc, ça donne lieu à des équations différentielles qui sont, comme je l'ai dit tout à l'heure, qui ne sont pas des équations linéaires. Et Einstein l'a dit également d'une certaine manière en disant que les particules n'est pas autre chose qu'une bosse d'énergie très importante qui se déplace dans le champ électromagnétique avec la vitesse de la particule. Bon, autrement dit, en fait, ça revient à dire en gros que tout est du champ. Tout est du champ, et il y a des endroits où il est très concentré, et ces concentrations s'appellent des particules. Alors moi, je reste dans le domaine électromagnétique, hein, je ne parle pas de particules qui sont comme le proton, des particules qui ne sont pas élémentaires, où d'autres champs de force interviennent. Alors, je vais faire une proposition, j'ai fait une proposition qui s'appelle la quatrième, qui consiste à dire que le deuxième membre que j'ai évoqué tout à l'heure dans cette équation, en fait, il s'agit réellement de la densité de courant, et non plus simplement d'un phénomène gravitationnel, c'est ce qu'on appelle la densité de courant électrique. Hein. Donc, c'est un petit peu un postulat hein, que je fais, mais je propose d'identifier ce deuxième membre avec le courant électrique qui est connu, le courant électrique et le courant le champ, enfin, de manière générale, ce qu'on appelle la 4 densité de courant. Alors, et ça rejoint, enfin, ça contredit ça résout plutôt une remarque d'un mathématicien très connu du XXe siècle, qui était André Chauwix, qui a été un grand spécialiste de la gravitation d'Einstein, et qui avait dit le problème de la théorie électromagnétique, c'est que le courant électrique apparaît comme quelque chose d'extérieur, d'étranger au champ électromagnétique. On est obligé d'en tenir compte parce qu'il existe, mais on ne sait pas on n'arrive pas à le raccorder au champ électromagnétique. Or, ce que je fais, c'est le contraire, justement. Je dis que la 4 densité de EGC, comme je l'appelais, c'est du courant, c'est le courant électrique. Le 4 courant, c'est plus exactement la densité. Hein. Voilà, alors, donc, c'est donc le champ électromagnétique qui crée la charge et non plus le contraire. C'est quand même un petit peu étonnant, je l'accorde. D'accord. Alors, donc, les charges apparaissent comme ce qu'on appelle des bosses. C'est pas moi qui ai inventé le terme, hein, c'est un terme connu des physiciens, des bosses du champ électromagnétique. C'est exactement, je suis à leur passant, c'est exactement ce que Max Born et Leopold Infeld avaient dans l'esprit, ce que j'ai présenté dans la vue précédente. Alors, on va faire une application dans un cas très particulier, qui d'ailleurs qui n'existe pas vraiment physiquement, mais ça permet quand même d'y voir un peu plus clair. C'est un champ électrostatique, c'est-à-dire qu'il ne bouge pas dans le temps, et il est de symétrie sphérique, c'est-à-dire qu'il est centré sur l'origine des axes, et il n'a pas de direction privilégiée. Alors, quand on fait cette étude, il faut intégrer les équations d'Einstein, je ne vais pas sur ces détails bien entendu, et il faut en même temps que l'équation de Maxwell, avec le second membre que j'ai pris en charge précédemment. Bon. Et alors à ce moment-là, on trouve, il est étonnant, d'ailleurs j'ai eu beaucoup de mal de m'en sortir, parce qu'on s'aperçoit que ça ne change rien, la loi de Coulomb est toujours valable, et c'est comme si on n'avait pas fait tout ce que je viens de dire. La théorie classique, elle marche indéfiniment. Bon, alors c'était très, très difficile de comprendre pourquoi. Donc, je vais vous présenter la vue suivante, qui est la vue un petit peu fondamentale. Alors, en fait, dans ce qui précède, je l'ai signalé en passant, je ne sais pas si vous l'avez bien vu, mais le potentiel est une véritable quantité physique, qui n'est pas le cas dans la théorie classique. Donc, à partir du moment où c'est une véritable grandeur physique, elle ne peut pas croître indéfiniment, c'est impossible. Elle a forcément, à un moment donné, elle atteint une limite. Donc, je propose, encore une fois, que la norme, ce qu'on appelle la norme, c'est un vecteur, la norme de ce vecteur soit limitée. Alors, j'ai proposé, mais ça mériterait une explication plus importante, que ça soit limité à ce qu'on appelle le potentiel de Planck, qui est de 10 puissance 27 volts. Vous voyez que c'est énorme, c'est un champ électrique gigantesque qu'on est très loin d'atteindre aujourd'hui dans quelle que soit l'installation qu'on a. Alors, ça explique un petit peu tout ce que j'ai dit avant. Alors, c'est bien sûr un cas particulier, c'est vrai, mais ça donne quand même une idée de ce qu'on peut, des résultats qui vont suivre. Donc, je propose donc, c'est un petit peu comme la vitesse de la lumière, que le quadrivecteur, puisque c'est encore une fois, on est à 4 dimensions, du potentiel électromagnétique soit limité par la valeur, le potentiel de Planck, qu'il ne puisse pas dépasser. Alors, dans ces conditions, eh bien, à ce moment-là, on peut dire que la charge électrique, ce qu'on a appelé la charge électrique, était confinée dans une petite sphère d'un rayon pour lequel on a atteint le potentiel de Planck. Donc, on ne peut pas, en dessous de ce rayon, le potentiel augmenterait encore, mais il ne peut plus. Donc, les lois de l'électromagnétisme ne sont valables qu'en dehors de cette petite sphère. C'est là la planche un petit peu fondamentale. C'est que quand on étudie le champ de gravitation autour de cette bosse, on s'aperçoit qu'il est répulsif. Alors, pas longtemps, parce que dès que la distance augmente, alors il décroît très très vite, et en plus, il s'annule à une distance, bon, je ne vais pas insister, c'est pareil, il faut rentrer dans les calculs, à une distance qu'on appelle le rayon classique de l'électron, et il redevient attractif au-delà, c'est-à-dire il passe par un minimum en fait, et il remonte attractif, et il tend asymptotiquement vers la loi de Newton que tout le monde connaît. Et ce qui est essentiel aussi, c'est qu'il ne dépend pas du signe de la charge, parce que ce champ est affecté par le carré de cette charge, et non pas par plus ou moins affecté. Il y a des électrons, il y a des positons. Alors évidemment, j'ai traité un cas très particulier. D'ailleurs, ce n'est même pas un électron que j'ai traité, parce que l'électron doit un spin, tout le monde sait, qui est une caractéristique essentielle de l'électron, et que je n'ai pas mentionné pour la bonne raison que je suis dans un système totalement statique. Donc, l'électron que je propose, c'est un électron classique qui ne met pas en cause la vision qu'on a en mécanique quantique, qui est à la fois une onde et une particule. Et ce qu'il faut se rendre compte, ça c'est assez curieux, c'est qu'à la surface de la petite microsphère dont j'ai parlé, l'accélération de gravitation atteint une valeur phénoménale, qu'on peut du mal d'imaginer, qui est de l'ordre de 10 puissance 53 millisecondes carrées. Mais elle décroît très très vite et devient totalement négligeable bien avant que le potentiel gravitationnel s'annule. Alors, il y a un deuxième problème que j'ai essayé de traiter. Mais alors là, je vous demande de l'indulgence parce que c'est un exercice de style. J'y crois pas beaucoup moi-même. Ça a rapport à ce qu'on appelle l'énergie noire. Alors, l'énergie noire, il faut savoir qu'elle a été découverte. C'est pas une découverte, l'expansion de l'univers, pardon. On passe de l'électron à l'astrophysique. L'expansion de l'univers a été découverte au début du siècle par Friedman et puis Hubble, avec la fameuse constante de Hubble. Mais par contre, ce qui a été découvert beaucoup plus récemment, c'est que cette expansion s'accélérait. Et c'était inexplicable. Et d'ailleurs, ce l'est toujours. C'est inexplicable. Alors, beaucoup de théories sont proposées. Il y en a une de ces théories qui propose que l'univers est rempli d'une énergie exotique qui aurait pour propriété de base de créer de la gravitation répulsive. Bon, ce qui paraît très bizarre, mais donc ça fait partie des théories qui sont étudiées aujourd'hui. Elle remplirait tout l'univers, mais ce qui est étonnant aussi, c'est qu'elle représente la majeure partie de l'énergie de l'univers, qui est quand même curieux. En plus, je ne suis peut-être pas sans savoir qu'il existe une deuxième forme d'énergie qu'on appelle la matière noire, et qui remplit, elle, 25% du volume de l'univers, ce qui fait qu'il nous reste la seule énergie que nous connaissons sous forme de matière, les étoiles, les planètes, etc., les gaz, la poussière et les rayonnements, ben c'est 5% de l'univers, c'est-à-dire qu'on n'en connaît pas grand-chose. C'est pour ça que c'est très spéculatif et que alors on a essayé de le comparer à ce qu'on appelle le vide quantique, mais pour l'instant, c'est pas très clair. Voilà. Donc, alors, j'en profite pour dire qu'il y a évidemment des gens qui imaginent qu'on pourrait utiliser cette énergie pour faire des voyages interstellaires. Bon, mais ça, c'est quand même de la science-fiction, parce que personne ne sait comment s'y prendre. Bon, alors donc, j'ai essayé de voir ce que ça donnerait si on remplissait l'univers d'un ce qu'on appelle un gaz de Bosch. C'est-à-dire, alors on s'aperçoit qu'on a un gaz constitué, enfin, on pourrait imaginer qu'il y a un gaz constitué de particules élémentaires, alors certaines positives, certaines négatives, chargées, hein, et qui seraient suffisamment faibles et suffisamment proches l'une de l'autre, pour que finalement on reste dans cette zone que j'ai décrite pour l'électron, où on est anti-gravitationnel. Alors, on trouve effectivement des particules comme ça, mais sauf que on ne voit pas comment. Personne ne sait qu'elles les a découvertes. Ça n'existe pas pour le moment, en tout cas. On ne les a jamais détectées. Donc, j'en termine. La difficulté d'une théorie comme la mienne, c'est qu'il faut la prouver, comme toutes les théories. Une théorie qui n'est pas validable par l'expérience, on peut la mettre tout de suite au panier et c'est bien connu. Bon, donc, comme il faut créer des champs gigantesques, ben, c'est difficile d'y voir clair. Alors, on peut essayer de le faire à l'échelle des particules, c'est-à-dire des électrons, les WIMPs, les particules de matière noire, là, tout à l'heure, la dark energy, donc, dont on a parlé. Et puis, à notre échelle, il y a quand même des gens qui ont des idées. Il y a un physicien mexicain, Pierre, qui a créé une métrique un peu particulière qui permettrait de modifier la gravitation, etc. Il y a un chimiste russe qui s'appelle Eugène Pokletnov, qui a prétendu, à la fin du XXe siècle, avoir modifié la gravitation avec un disque supraconducteur. Bon, mais on n'a jamais réussi vraiment à refaire son expérience. Et puis il y a aussi Raymond Piccoli, qui fait partie de notre CRD, et qui, lui, s'occupe des phénomènes un peu bizarres liés à la foudre. Et puis il y a aussi l'échelle cosmique, qui est beaucoup plus. On change d'échelle, qui sont des étoiles qu'on appelle les magnétars, qui sont pas très. Qu'on a découvert récemment, et qui, comme leur nom l'indique, génèrent un champ magnétique très très élevé. Voilà, j'ai fini mon exposé. Donc, la seule chose que je peux conclure, c'est que moi, je suis pas chercheur de métier. J'ai fait ça parce que je pense que j'ai travaillé dans le spatial et je pense que les fusées actuelles sont quand même très limitées pour tout un tas de raisons, même si Elon Musk en est occupé, et que un jour, il faudra trouver autre chose. Malheureusement, on ne voit pas beaucoup d'autres manières d'y arriver qu'à modifier la gravitation. Voilà. Merci.
So I propose that we continue with the next presentation.
The second talk of today is by Olivier Goretta, who is an engineer and is working with the Aeronautical Association 3AF and its well-known Sigma 2 Commission. He is a specialist in radar phenomenology and similar topics. His speech will be about a review of science applications to propulsion and defense intelligence reference documents related to another well-known institution that came onto our scene, that is the AATIP or AAWSAP, the Advanced Aviation Fleet and Identification Program within the American Defense Organization. So you can go on.
Hello, so that is a presentation on the review of science applications to propulsion and defense intelligence reference documents related to the IATIP and AOSAP. So first, we are going to deal with science applications to propulsions. The Sigma 2 Technical Commission explores a novel approach in order to have some hint to try to explain UAP behavior and which technologies could explain these behaviors. So the analysis of documents related to technologies in advanced or breakthrough propulsion, but not only propulsion, is part of the job. And so Sigma 2 experts, including the late Dr. Paul Kunzmann, have analyzed several theories that could explain UAP behavior. And we are going to see that in the next slide, please. So there are four fundamental forces. So gravitation, of course, electromagnetism, the strong and weak forces. With this force, we have theoretical basis to explain what they are, where they come from. So we have Maxwell's equation for electromagnetism, general relativity that can describe the massive corpse behavior, and quantum mechanics for the elementary particles. There are two main approaches to search for what we could call scientific breakthrough: the experimental approach and the theoretical one. And based on these approaches, a number of steps have been studied by Sigma 2. So these are the steps that have been studied. So limits of interstellar flight technology, prerequisite for space drive science, gravity control within Newtonian and general relativistic physics, gravitational experiments with superconductors, electrogravitation, the Biffle-Brown effect, propulsive implication of photon momentum in media, thrusting against the quantum vacuum, inertial mass from stochastic electrodynamics, relativistic limits of spaceflight, the faster than light approaches in general relativity and their implication of quantum entanglement and non-locality, comparative space power guidelines, try to extract energy from quantum vacuum, investigating sonoluminescence as a means of energy harvesting, and general relativity computational tools and conventions for propulsion. So the provisional conclusion of this step studies, first, modern science is not an achieved endeavor, since we have still difficulties to reconcile general relativity and quantum mechanics. With that, electrogravitation does not seem to work. Right now, no propellantless propulsion has been demonstrated. We have contrasted results for quantum mechanics, with, for example, the Casimir effect. And apart considering space-time engineering with a warp drive, Stargate, wormhole, or a virtual space-time vehicle, the current state of our science implies that UAP propulsion can only come from a combination of two, into brackets, conventional technologies, magneto-hydrodynamic propulsion, or one of its variants, combined with a nuclear power source by fission or fusion. These are the only way to explain UAP behaviors, of course, considering also space-time, what I call the space-time engineering. So among the documents surveyed by Sigma 2 are the AATIP AOSAP Defense Intelligence Reference Documents. These documents have been made public thanks to FOIA request, which was filed by John Greenwald. They are available at the link displayed on the slide. I recall what the AATIP and AOSAP meaning. So AATIP was Advanced Aviation Threat Identification Program, and AOSAP was Advanced Aerospace Weapon System Applications. In fact, they are the same program. AOSAP seems to be the official name, and AATIP was also a name that was used for the program. So the DIRD documents can be classified in several categories. So the categories are as displayed on the slide: materials, biologic applications, energy sources and laser, advanced classical propulsion. In this propulsion, I will put MHD, EHD, and things like nuclear propulsion. Breakthrough propulsion is related to the engineering of space-time, generally speaking. Advanced control and man-machine interface, breakthrough communications and computing, detection, and sociologic aspects. In the following slides, I will talk about or list the different documents that are related to each category. So for materials, we assess status and prospects for aerospace applications, aerospace application of programmable matter, materials for advanced aerospace platforms, invisibility cloaking, theory and experiments, metamaterials for aerospace applications. The number you can see before the document is the number of the Defense Intelligence Reference Document. So for biologic applications, we have biomaterials, biosensors and biomems, a survey of the present field, and anomalous acute and subacute field effects on human biological. On this particular aspect, it's very interesting since we have a medicine doctor within Sigma 2, and we have made some studies also on the field effect on human. Energy sources and laser. So we have 4 documents on energy sources: pulse high power microwave source technology, inertial electrostatic confinement fusion, concepts for extracting energy from the quantum vacuum, and ultracapacitors as energy and power storage devices. For laser, we have state-of-the-art and evolution of high-energy laser weapons. You will see that for the energy source, we have rather, let's say, classical technologies, and one which is really a breakthrough technology, which is extracting energy from the quantum vacuum. For advanced classical propulsion, we have several documents. The first is space access, where we have been and where we could go. Positron aerospace propulsion, advanced nuclear propulsion for manned deep space missions, laser lightcraft nanosatellites, aneutronic fusion propulsion, magneto-hydrodynamic MHD, air breathing propulsion and power for aerospace applications, and aneutronic fusion propulsion too. So these are what we could call advanced classical propulsion, which are nevertheless beyond the current science and technological situation of today, but we could, with some little advance, put them into working, but they are different from what I have called the breakthrough propulsion, which are really related to really disruptive technologies. So the breakthrough propulsion, we have things that are, as I said, really disruptive: warp drive, dark energy, and the manipulation of extra dimensions. The role of superconductors in gravity research. This is perhaps the less breakthrough-like document in this part. Advanced space propulsion based on vacuum space-time metric engineering. Traversible wormholes, targets, and negative energy. Anti-gravity for aerospace applications. negative mass propulsion, and quantum tomography of negative energy states in the vacuum. Advanced control and man-machine interface. So we have 3 documents. The technological approaches to controlling external devices, cockpits in the era of breakthrough flight, and cognitive limits on simultaneous control of multiple unmanned spacecraft. The last is almost a study for today. It has to be said that at the time this last document was done, artificial intelligence was not as advanced as it is today, but nevertheless, the document is interesting. So breakthrough communication and computing. So for communication, we have the space communication implication of quantum entanglement and non-locality, which discuss the possibility of instantaneous communication, high-frequency gravitational wave communications, and on the computing part, we have metallic spintronics and quantum computing and utilizing organic molecules in automation technology. So both are using quantum technologies. But what is interesting with the second one is that it is a kind of synthesis between quantum technology and organic use of organic molecules and ADN in order to make computations. For detection, we have only one study, one document, detection and high-resolution tracking of vehicles at hypersonic velocities. It is a rather conservative document compared to all the other documents of all the defense intelligence reference documents. And it seems to explain why today we have some difficulties to detect and track hypersonic vehicles. So what I have called sociological aspects. So maverick inventor versus corporate inventor, where will the next major innovations arise? So it's a study on how could we try to see where the next innovation will come from. So quite interesting. And an introduction to the statistical Drake equation. Drake equation is the equation that describe how we can try to calculate the statistical chance to get another advanced and technological society, and it's a good way to try to analyze how we could where we should look to find another extraterrestrial civilizations. So the last slide is in fact an example of what we can produce as a data sheet for on the different defense intelligence reference documents. So the example is for the MHD air breathing propulsion and power for aerospace applications. So magnetohydrodynamics has a performance potential beyond that of conventional propulsion, because the energy is not related to the mass of the propellant. And one of the main challenge for MHD is ionization, the ionization rate. on this document, we can take three main interesting concepts and applications. The Ajax concept with endothermic fuel conversion, energy bypass, and use of plasma for drug reduction. Another interesting concept is the reverse energy bypass concept, where the energy is extracted from the flow in an MHD generator placed downstream of the combustor. The question is it applicable to an Ajax variant? And the MHD application to re-entry and to near Earth orbit, thanks to the atmosphere that surrounding a re-entry vehicle, then it's easier to use MHD because the atmosphere is naturally ionized, and it's because of the heating during the re-entry, then the ionization rate is quite interesting. The conclusion of the DIRD document is that MHD propulsion is apparently today still beyond the scope of the applications described. So it would require the generation of very high levels of energy to create an MHD thrust that could replace any other form of thrust. So there is a little work to do anymore. And nevertheless, with the content and the results of this defense intelligence reference documents, we can infer that a more advanced technology should be able to use MHD propulsion and nuclear power to achieve characteristics similar to those of some UAP. And so we get to the same conclusion as with the space propulsion studies one. And what is interesting, and I didn't put it on the slide, but nevertheless it's something interesting, is that when you when you ionize the atmosphere, the gas surrounding the craft, the ionization of nitrogen can generate a signal at the frequency of 3 gigahertz. And in some of famous UAP events, such as with the RB-47 that was followed by a UAP, in this case, there are the presence of this 3 gigahertz signal. So perhaps it could be perhaps something that could make us think of an magnetohydrodynamic propulsion, but there could be also other explanations. So that should end my presentation. Thank you. And I'm ready to take questions.
Okay, another technical paper. Let's see if there are questions.
I have a question, Edoardo.
Okay, Robert.
So one of the characteristics of UAP is extreme linear acceleration and extreme angular acceleration. Which of the methods that you described could explain those two characteristics?
In fact, the methods that could explain those characteristics could be perhaps a combination of MHD or EHD propulsion with perhaps a forced propulsion. That means a kind of jet coming from the vehicle, which is used on some kind of missiles, iron missiles today. but I think that the best explanation when you have very strong accelerations and right angle turns and things like that, for me, the best explanation is the engineering of the space-time metric. I don't know if that answers your question.
Yes.
I think this is an open question. We don't have we don't have any conclusion on our side. Why? Because we feel that some techniques could be of interest to explain the capacity to reach very high velocities, the capacity to maneuver without inertia effects, and so on. There is also the presentation that was made just before by Pierre Marx on the gravitational control and so on. But anyway, none of these theories are demonstrated one way or another. We would need some experimentation to see what is the way to try to reach someday this kind of performance. At the opposite, and we can come back to the other subjects of the sessions, there is the question about the observables. Okay, the observables can be a way to pave the way to identify theory or demonstration of theory, to have indication, if you wish. If you observe, you know, the main discovery in science, okay, people were observing the surrounding, the nature, and so on. And by number of observation, they try to figure out, maybe with full intuition and so on, the mathematical law that could be applied to a model. And then demonstrating the model, at least locally in the environment where they were. This is exactly what is missing. That's gathering indication, information, and so on, to try to see, you know, what is the possible law or theory, and that's one of the main issues.
What I can add is that also perhaps there is the problem of the occupants, if there are occupants in a vehicle, because if you have a kind of drone, even with MHD and with some other applications, you can perhaps manage to get very maneuverable vehicle and with quite strong acceleration. But the problem is if you have people in it, whatever they are, then you can come to a problem. I remember that in some movie they put some liquid, respirable liquid, visible liquid in the cabin. So is it really a way? I wonder if there has been tests to see if there is something living. I think of a fish, for example, in the cabin of a vehicle. Can it withstand very strong accelerations? I don't know if it's a solution. And of course, if it's the engineering of space-time metric or wormholes or things like that, then you don't have the problem, since the occupant of the vehicle are not submitted to the forces because of the motion of the vehicle.
The other method you mentioned, inertial mass, although we don't know if it's possible, if you can reduce the inertial mass of the object and the occupants towards zero, then that solves a lot of your problems.
Exactly. You can either reduce the mass, that means you reduce, normally if you reduce the mass, you reduce the inertia or the other way is if you in fact within a kind of space-time bubble, in fact, you don't move, then there is no inertial effect.
I also have a question. When you mentioned in the Drake equation, you said that artificial intelligence, which has progressed now, might help. But if I'm not mistaken, the Drake equation's parameters are all probabilistic. So how could artificial intelligence help?
Perhaps I think that artificial intelligence, AI, could help for some parameters, for not all the parameters. That's the problem of the Drake equation, is that in fact, you say the main parameters are probabilistic. But AI could help to get let's say, the most probable parameters, and so perhaps it could help us to have an idea to where we should look. In fact, it's just a kind of guide. It's just to guide us, guidance to help us to look there instead of here. But it's just that. Okay. Because the main problem of this equation is the parameters that are unknown. But nevertheless, if you take a look at what was the situation when Drake established his equation, and today there are a lot of parameters, and now we know that planets are quite common. At the time, it was not evident, it was not known, and so with the time, we will get more and more precise parameters, and we can perhaps manage one day to have a true equation. Let's dream about it.
Thank you.
If there is no more questions. Aha, I see a hand out of field. Baptiste, I suppose.
Have you read all 38 DIRDs?
Sorry.
Have you read all 38?
No. I have not read all the documents. I read at least the abstract, but in fact I read 2/3 of the document. For 1/3, I just read the abstract because I didn't have any time before the.
No worries. Do you think these are real scientific white papers, or they are just ideas put on paper that what could be, but are unverifiable?
Thank you for this question, because it's very interesting. These documents, this is my personal feeling about them, but I think that these documents make me think about what I could call feasibility documents. In fact, they are documents that study some parts to see if it's worth investigating or not. Mm-hmm. For me, that's their main purpose.
And what is their conclusion? Do they mainly think, yes, it's a valuable path of study, or they discard it in the paper?
No, so some are valuable. Some are valuable. The one that really disappointed me was the one on the detection. Mm-hmm. My personal feeling is that, in fact, there are other documents that are still classified today. But for the rest, I think that they are, like I said, feasibility documents that needs further investigation. Mm-hmm. And if I remember well, it's consistent with the story of these documents.
Yeah.
And of the IATIP and OSAP programs.
They are now 20 years old, I think, something like that.
No, not 20 years old. They date back 2010 or 2011, 12. No. So they are quite recent.
Okay. 15.
No, in fact, when you read the world documents, the feeling you have is that the only thing they missed, if you can say that they missed something, is the current development of AI, mm-hmm. of artificial intelligence. for the rest, and except for the detection part, they were quite interesting document considering the way science and technologies has advanced on these topics.
Thank you.
Yeah, just a remark about the papers and the one that you mentioned, the last one about the hypersonic vehicle accurate tracking. The point is that these papers are back, 15 years ago. And if you take the subject of hypersonic missile, it was nearly unidentified in 2008. If you remember, it was the very beginning of, because of the Obama administration, of the prompt global strike and so on. So that was the first moment. Of course, there were research before, okay? But in the open, it's just when people say, hey, I would like to be able to strike anywhere on the planet within 1 hour, okay? That was the slogan at that moment. So, of course, 15 years later, 16 years later, a lot of things happen. Some Russian missiles and so on, other research maturing, and the subject in terms of physics, which was known of some people but not, broadly, is now expanding. So the vision and the knowledge today can be compared, and especially in a white paper, in the open and so on, to the knowledge of today about hypersonic missile, or the knowledge of some experts working at the moment on some missiles, on re-entry vehicle, and so on, because it was techniques and science which was not so much shared. That's and the technology of sensors has changed. If you take, for example, the problem of detection and tracking, if you think of the presentation of yesterday morning from ICANN, we have put in orbit some small satellites in 2009, okay? But today, having small satellites and so on in orbit is something very common, okay? The idea of having a constellation of small satellites to track whatever, UFO, missiles and so on, is something which becomes more and more credible. 15 years ago, it was another matter, I think. And it was not so obvious. No, but
no, you're right. But let's say that in certain space circles, there were already thoughts about this kind of satellites. And I think of René Blamont, for instance, from the French space agency, which was pushing quite strongly the little satellite. And what I wanted to say about this document is that for me it was a surprise, because you had all the other ones. You had things that were really, let's say, a bit exotic. And this is the only one where I don't see anything exotic, so that was quite surprising. That's perhaps this is my feeling about it.
Okay. Are you familiar with the OSAP research they conducted in the US?
What do you mean by familiar?
The various projects they worked on.
I know them a bit, but I didn't work on that. So
it's just that I find it funny that OSAP had definite projects they were working on, and what they sent to the DIA were these files, where they hired outside contractors or scientists to make feasibility reports,
exactly.
term, but they are almost completely disconnected from the data they gathered inside their own projects. So is that something usual for example, NASA hired an audit group on UAP to be separated from
the problem. I think that we cannot answer this question. Why? Because when you produce a report for an administration, here it's for the DIA within the DOD, that means that you have a contract.
Mm-hmm.
If you don't know what is in the contract, you don't know what was asked, what was the question asked. If you don't know the question, then it's difficult to give an answer considering the answer in the report.
Mm-hmm.
Well, I suppose we can go on with the last paper in the afternoon before the roundtable. And if I got it right, we come back from theoretical approach and feasibility studies that, as Baptiste was saying, it was seemingly unconnected with the real UAP data. We come back to a work which is, on the contrary, coming back to data. Study and analysis of UAP data. The authors are two. They are both Americans. Dr. Sarah Little is holding a PhD from the Massachusetts Institute of Technology. Is coming from oceanography, but has worked both on underwater acoustics and on visual adaptive optics. And as such, she has co-authored some projects, some papers for the Galileo project. And most of all, she is an advisor, a science advisor of the Scientific Coalition for UAP Studies. The second author is at the heart of the Scientific Coalition of UAP Studies because Robert Powell is a founding member, is on the board of this organization that is aiming to bridge science and UFO investigation. He comes from chemistry, but is an engineer and author of several papers in our subject. And today's contribution starts from a large database of UAP reports with a tight selection of relevant cases and goes from shape, size, kinematics up again to this morning subject of electromagnetic effects and sound.
Thank you, everyone. And I will be discussing a paper from the SCU that was peer-reviewed within the SCU. And this paper is the reported shape, size, kinematics, electromagnetic effects, and presence of sound of unidentified aerial phenomena from select reports 1947 to the year 2016. Slide. Let me tell you first a little bit about SCU. SCU is a 501c3 nonprofit organization in the United States, and it was founded in 2017, so it's almost 7 years old. It consists of over 300 members today, which are mostly scientists, engineers, former military officers, forensic investigators, and it includes people from many different industries, such as NASA, European Space Agency, Lockheed Martin, Sandia Labs, NORAD, many people from the high-tech industry, and university professors. Almost 30% of the membership have PhDs, mostly in the scientific fields, and 20% of the SCU membership is outside of the United States. So it is truly an international organization. Slide. The authors of this report, myself, I have a bachelor's in chemistry. I'm an executive board member of SCU. I'm an author, and I've spent 17 years studying the UAP subject, and I would say an average of 20 hours per week during those 17 years. Also, is Sarah Little. She has a PhD in marine geophysics, and she is the SCU science advisor and will be joining us today in the roundtable discussion. Larry Hancock, with the BA in History and Cultural Anthropology and is a member of the SCU board, is also one of the authors of the paper. And then we have 3 individuals from the University of Toronto. These are graduate and undergraduate students that have worked with SCU on this paper. Those include Laiba Hassan, who did some of the artwork that you will see in my presentation, Robinson Trong, and Toby Kamoru. Slide. Let me give you just a brief overview of some of the UAP reporting history and database that exists today. And the military databases, and these are just some, there are more than these, but the primary ones are from the United States, United Kingdom, Canada, Australia, New Zealand, Brazil, and of course, France. And of those, the French database, and when I say military, it's not truly military, it's CNES, which is part of the French space program, but I've just put it in this category because it's not a civilian system. It is the only one that currently is still collecting data today of the military databases that I listed. Of the civilian databases that you see on the screen, these are all United States civilian databases. APRO, NICAP, CUFOS, MUFON, and NUFORC. Those are the primary sources of UFO information in the United States. Now, there are obviously many other civilian databases in other parts of the world, but this paper primarily relies on United States data and some French and Canadian data and Australian. Next slide. One of the problems with all databases is the quality of the data itself. Most UAP reports, as those of you who are familiar with this subject are very aware, include misidentification, hoaxes, and insufficient data. Those really are what drive the vast majority of UAP reports. The true unknowns, or UAPs, that we cannot explain, are much less. Project Blue Book estimated less than 6%. Hendry estimated less than 9%. All the work I've seen is also in that same area. So this means that more than 90% of the reports in these databases are not real reports of true unknowns. They're aircraft, stars, planets, what have you. Slide. So for this list of historical shape analysis, these are some of the reports that have been done in the past. If you look at this and you look at the bottom of this slide, you'll see there's only one report historically that's been done that filtered the database before it looked at shape distributions. And that was the Battelle database in 1955. And they used the Project Blue Book database. And you can see the primary shape they had was elliptical. But if you look above there have been many reports where the database is unfiltered. So that means that 90% and more of the data that's in the report is data that we know are known objects. So this type of data doesn't really tell you anything about the shape of the object because the data is unfiltered. And as you can see, as you look at the slide, there's everything from spheres to disks to star-like. And take, for example, the Arrow report, the most recent one. Many of you may have seen this report, and there's a chart, and it shows that the sphere is the dominant shape. Yet within that same report, they tell you that over 90% of the shapes are basically of known objects. So when you say the sphere is your basic shape, really doesn't mean anything because you do not know what is the shape of the true unknowns. That is really telling you the sphere is the most common shape reported, but it's not the most common shape for UAP. And as I said, Battelle is the only one that's been done to date. Now in our paper, we are doing the same thing. We are filtering the data before we examine the shape distribution. Next slide. So these are the databases that we used. We used the Project Blue Book report, which covered the years 1947 to 69. We used some of the reports out of GPON. We used reports out of NICAP, which were from 1956 to 1980. Some reports from CUFOS, and reports that came through the MUFON system, which was 1969 to present. All total, those databases are about 100,000 different reports. Now, we have filtered those down to 301 reports, and in a moment, I'll tell you how we filtered them. But I think it's important to realize that someone else could go through the same database with the same criteria we used, and you might come up with 400 reports or 200 reports, but it will be in this basic range of reporting. So next slide. So the question is, what were the criteria we used to thin down 100,000 cases down to 301 cases? The overriding driver was that we used UAP data cases that were first screened for unresolved candidates by selecting reports that have been investigated and curated. So in other words, if an individual makes a report of UAP and no one investigated it, we do not use that report. So of your 100,000 reports, especially those in the MUFON database, which makes up a large percentage of the 100,000, if there was no official investigation and all we have is the report itself from a civilian witness, that would not have passed our filtration system. Okay, so then you have a much smaller number once you look at cases that actually have reports. One of the first filters we used was the reliability of the observations. So we looked for multiple witnesses and or a high quality witness. High quality being, for example, a policeman or a pilot, someone who would have had to reported to their superior as to what happened. Second, we look for the nearness of the object, a minimum of 0.15 degrees of angular size in the sky. The moon, for example, is roughly 3 times that. So in other words, an object in the sky that was at least 1/3 the size of the full moon, which means that the object is close enough that you minimize the possibility that the witness is misinterpreting what they are looking at. The third filtration point was sufficient lighting. So the bulk of our cases are daytime cases. The only nighttime cases would be if there was sufficient lighting from the object itself or the ground to light up the object. And lastly, there has to be sufficient detail in the report that was written that we can draw some conclusions such as the shape, distance to the object, angular size, etc. Once all those criteria were met, we came up with 301 case reports that met these criteria as filtered by 3 different individuals. So at least 2 out of those 3 individuals had to be confident that those 4 criteria were met. Next slide. So this paper, we examine the shape of the object, its estimated size, its kinematics, EM effects, sound, and effects on the environment. Next slide. Data and characteristics that we collected, but we will not examine until a future paper, are items such as date, time, latitude, longitude. In other words, we did not look at time and physical location in this particular paper. This paper is specifically about shape characteristics and those relations to things such as EM and sound. So a second paper will come in the near future. Next slide. Shape was chosen as the primary characteristic. And, you know, we are aware as we wrote the paper that there are considerations on shape. For example, the viewing angle can affect the shape that a witness sees. A disc, if looked at directly up above or directly below, could look like a sphere. The same thing for a disc. Seen from the side, the proper angle can look like a cigar shape. So that was one issue, the viewing angle. The other thing that affects the shape is the nomenclature that the witness uses. One person may call a disc a circle. Another person may call a triangle a delta-shaped object. Another individual may call a cigar a cylinder. So we took that into account as we wrote the paper. The most frequent occurring shapes that we found of the 301 cases, the disc was predominant at over 1/3 of the cases. The second most common was the triangle at 11%. The oval, which, you know, some of that can be discs, right? But we kept the part that the witness used the term consistently oval and left it there, and that's 8.6%. Spheres, 6%, cylinders after that, and then the delta shape was the sixth most common shape. Next slide. So we created a table, and I won't go through everything in the table, but it shows the shape, the percentage of the 301 cases that met that shape, and an approximate size. And as long as we had at least 3 reports, then we would estimate the size range for that particular shape. One thing that I want to mention there is that you'll notice the smallest of the shapes was always the sphere. And the largest shapes, and some of you may already would have guessed this, are the rectangle or diamond shape, the boomerang, and the triangles. Those are normally the larger shaped objects. Next slide. So our most common shape was the disc shape. And the disc, and we divided that into 2 types, is the disc with the dome and the disc without a dome. The disc with the dome, normally if you looked at the diameter, the ratio of diameter to height of the object, you're normally looking at a 2.5 to 1 or 3 to 1 ratio. And the size varied roughly from 20 to 40 feet in diameter. The other type of disc, as we defined, is without the dome. And there were 2 types, basically. There's a short version, which has a ratio of 2.5 to 4 to 1, somewhat similar to the one with the dome, but a little bit larger in a range of 30 to 60 feet. Now, the elongated disc, this is where you have a ratio of 5 to 10 to 1. So a much longer craft compared to its height was also a much larger craft. Usually it was identified as 100 to 150 feet in size. And then, of course, the triangles, which is the second most common category. And it was basically split into 2 groups: isosceles triangle reports and equilateral reports. The isosceles reports were usually a ratio of 2 to 1 of the base to the length. And the object size varied considerably from 30 to 300 feet. Probably the more unique thing about the isosceles is that it's normally reported to have multicolored lights. And there was really, we found no consistent pattern of lights when someone reported an isosceles triangle. The equilateral triangle, however, is very different. That is very consistent pattern witness to witness. It's usually 100 to 150 feet on a side. There's almost always a light at the vertex of the equilateral triangle. And in the very center, there's often a smaller light sometimes reported. but the vertex lights are always are much more common, and then sometimes a light in the center. Next slide. So Leba Hassan did the artwork for us on the construction of these object shapes. So this is the disc with the dome, which I talked about first. And there you see the size variance of 20 to 40 feet, 8 to 16 feet in height. So basically a ratio of 2.5 to 1 of diameter versus height. Now on the next slide, you will see something that looks very similar to this. Next slide. This is actually a shape reconstruction done by the Battelle Institute, which, remember, it was also filtered data. They looked for what they considered to be the true reports of unknowns. And this looks very similar to the slide I just showed you. It is an object of about 20 feet in diameter, 6 to 8 feet in height, and appears to have a dome type shape to it. Next slide. Now this is the disc without a dome, and it's a ratio of 3 to 1. So in the diameter is normally 30 to 60 feet with the height of usually 10 to 20 feet, which if you probably shrunk the ratio to maybe 2 to 1, you could almost call this an oval shape. On the next slide, we have the elongated disc. Now the elongated disc is normally much larger. It has a ratio anywhere of 7 to 1 to 10 to 1. A 7 to 1 is what we use in the drawing because that's the more common. A size of 100 to 150 feet, and a much higher height of 15 to 20 feet. Next slide. Now the triangle, the reconstructed appearance of that, this is the isosceles triangle. And as you can see, the length is normally in the neighborhood of 200 to 300 feet. The base 100 to 200 feet. So this is a large size object. This is roughly the size of a commercial airliner, and a thickness of 20 to 30 feet. And of course, the most consistent of all shapes is on the next slide. And this is the equilateral triangle. Many of you are familiar with this with the Belgian waves of the late 1989 and 1990. This has a light at each vertice and often a small light in the very center. The size of each side of the triangle is 100 to 150 feet, and the lights are normally quite large, around 6 feet in size at each vertice. Next slide. So these shapes with multiple characteristics. I want to talk now briefly about what we saw that related to the shape. And let's begin with the disc. The disc normally showed the ability to hover and also showed indication of extreme acceleration. Extreme acceleration is what we mean by acceleration that's beyond what a normal military aircraft can accelerate to. Most military aircraft, pure linear acceleration is no more than 2 g-forces. Now, when you talk about angular acceleration, it could be around 8 to 10 g-forces. But here we're talking about linear acceleration. The disk also has a unique characteristic that's often reported, that it can wobble, it can spin, either there's no sound or there's a very light hum, and EM interference has been reported with a disk. Now, bear in mind, of these 301 cases, when I say it has this characteristic, that does not mean that it cannot potentially have another characteristic. These are simply the characteristics that have been reported. The triangle, 32 of 33 reports of the triangle, and that's out of that total of 301. Of the 33 triangle reports, every one except one reported hovering, which is unusual. In other words, everyone, when they see a triangle, it's not just flying by. They usually see it sitting still in the air. It also usually has extreme acceleration. And we had actually 2 or 3 reports of a triangle that would actually spin. So talk about non-aerodynamic. That is a very unusual report to hear that. It either has no sound or very slight sound. And this was an interesting characteristic that we did not expect. There was not a single case of EM interference of the 33 reports that we had filtered out. Now, maybe somewhere out there in the vast reports, 100,000 reports, someone has reported a triangle with EM interference, but that appears to be very rare if it does occur. So that was a unique characteristic that we found with the triangle. Oval-shaped objects, very similar to what you see on the discs. Hover and extreme acceleration, wobbles, spins, no sound, and this was a little bit unique to some of the oval reports of oval-shaped object, was a loud noise. We never had reports of loud noise in our 301 database cases with the triangle or the disc, but we did with the oval shapes. And the oval shape also had EM interference reports. Next slide. So in discussion, the Battelle report is the only historical shape study prior to our current report that we've written, where selection and filtering of reports was clearly undertaken. For the future, we believe the use of natural language processing and the use of AI are both good techniques that can be used to filter large databases to look at reports that are more likely representative of true unknowns. And we believe more of this needs to be done and more analysis using filtered databases, not unfiltered databases. An unfiltered database tells you more about the characteristics of the people that report these sightings. It doesn't tell you about the sighting, it's the actual phenomenon that makes up what we call UAPs. This data that we've put in this paper, these shape characteristics that you saw, that could be learned, for example, could be used, for example, to shape and guide AI searches, for example, on satellite scanning systems. So you could program the AI to look for these specific shapes. It could also be used to optimize synthetic aperture radar, which can return object shapes, but you have to take the raw data and refilter it, because normally synthetic aperture radar is looking at the ground, but you have to look at the raw radar so that you're basically slicing through the atmosphere as you analyze the synthetic aperture radar. Next slide. So on conclusions, our approach minimizes the uncertainty in witness reports by selecting for the reliability of the observation, the object's angular size, that there's sufficient lighting, and sufficient information detail to draw any conclusions. The disk was the most frequent UAP shape, with the disk with the dome being a 2.5 to 1 ratio, 30 feet in size. Discs without dome come in 2 basic categories. You have your shorter aspect ratio, which is a smaller craft, and your larger aspect ratio, which came with larger sizes of 125 to 130 feet, more along the size of a commercial airliner. Next slide. The triangle, which was the second most common UAP shape, the equilateral was clearly the most consistent shape report, with the large circular lights at each vertex and the smaller light in the bottom center. The interesting part, again, was no EM interference related to triangles. And the other interesting thing about the triangle is the kinematic combination of hovering and extreme velocity. In other words, we have craft that can hover, right? An F-35 can hover, a helicopter can hover, and we have craft that can have high velocity. But we don't have craft that can both hover and have extreme velocity and then suddenly stop again. So for example, if you take the F-35, which might be the closest to match that, it can hover, but it's requiring extreme, it's very noisy when it's hovering, and it requires an extreme amount of fuel to be able to hover for those short periods of time. If it hovers for very long, it's going to run out of fuel. And then the extreme velocity, even an F-35, acceleration is going to be probably in the neighborhood of 1.2 to 1.5 G forces in linear acceleration. So it doesn't have extreme velocity from point when it's starting from the hovering point and moving outwards. It takes it quite a while to get to that high velocity. And that type of hovering in combination with extreme acceleration is very unique to the triangular shape reports. One that comes to mind was a report from 2 Memphis, Tennessee policemen who were looking at a triangular shaped object hovering, and it began to accelerate, and within 2 seconds, the object had disappeared from sight. And this is an object that's 100 to 100 feet in size and was fairly close to them because angular size-wise, it was fairly large. If you took a jet that had to go from a stationary point, such as an F-35, from stationary position to accelerate out of sight, you're looking at probably in the neighborhood of 12 to 15 seconds as compared to these objects, which do this in 1 to 2 seconds, an extreme difference. Next slide. So this combination, this unusual kinematic range in the absence of sound was found in 16 reports. So in other words, 16 reports where not only can the object hover and can the object move beyond Mach 1, but the object also provides no sound to the witness. A disk with a dome, we have 1 instance of that occurrence. Without a dome, 4 instances. And here's where the triangle was the most common. 8 instances of a triangle that hovers, goes to speeds that are clearly beyond Mach 1, and throughout the entire event, there is no sound. And then there was 1 instance with the oval, the sphere, and the boomerang. This appears to be a unique characteristic to some UAP. How many of the UAP are capable of this, we don't know, but we do know that this does happen, and it's a unique combination that you can't do with any known terrestrial aircraft. Next slide. So we would like to give thanks to Ike Alcafer of the University of Toronto. Ike helped us with the students, and the university supported the students in their work with the SCU. And also for anyone interested that would like to see the specific 301 cases we used in this paper, you can go to the Zenodo website, and there is the actual link that allows you to download all the individual cases that we used in this report. So thanks, and I look forward to our discussion at the roundtable. Have a great day.
An impressive work. Well, I ask Robert a question myself. Listen, what about the quality of the data you used? That is, all these databases, were they including a quality evaluation for each record, or it was only you who decided which reports were worthy to be retained and which not?
So good question, Edoardo. So we had 3 individuals, and we would rate each case, and we would give it a green, a yellow, or a red. And so if a case would require, for example, two or more greens in order to be considered, if it received, a single red from the 3 people evaluating, then it was rejected. Or if it received two or more yellows, then it was rejected.
So it was an evaluation that you had to do by yourself, based upon the available data.
Yes, myself, and then Larry and another guy by the name of Steve Purcell.
Because the typical problem with all databases, all UAP, UFO databases, is the quality of the underlying data, how it was collected, how it was stored, and so on. So you know well the case management system of the mutual UFO network. Each case is given an evaluation, at least since it is kept as such, but not all databases are including this kind of preliminary quality evaluation. So it's often difficult to work on this secondary or tertiary data for any analysis. This is a difficulty that we have always met. So it's interesting how you worked on such a large sample in order to extract a small but relevant subset.
Right. To speak to the MUFON database, for example, almost, I would say, less than 10% of their cases are actually investigated. So by an investigation, that means someone, actually does a true investigation. They don't just fill out a piece of paper and say, okay, I think this is an unknown, or this is, a hoax, or whatever. It requires an actual report.
Well, I am of the old school. Investigation by me means going on the place, talking with the witness, and taking some measurements on the place. If not, it's not a real investigation. It's an evaluation. Okay.
Right. And I would have to go count for exceptions to that, but I would say, Edoardo, that our 301 cases are basically where there's an investigator on site with the witness. In other words, they actually talk to the witness in person. There could be a few exceptions to that. I'd have to go back and look, but I'm sure the vast majority of ours are done in person.
Yeah, but I still think that it is worthy only for high strangeness, high credibility cases, or close encounters. You have not to lose too much time on distant lights in the sky. So in order to get a reasonably relevant subset of interesting cases to analyze, we still have to follow directly the cases if it is worth it. If it is promising. Yeah, I see that you consider the same thing as our local coordinator about physical effect cases, Stefano Innocenti. He decided to include sound cases, UAP emitting sounds, because he said it's an interesting feature that can be evaluated some way, but not everybody is doing that sort of consideration. That was why today in the morning I was enlarging the concept of effects on the environment, including non-visual perceptions, smells or sounds, and I was happy that you included sound emitting UAPs in your analysis.
I see Jeffrey has a question, I think.
I cannot see him. Where are you?
Yes, I'm here. Yes.
Oh, okay. Here.
Thank you. Good job, Robert. Very interesting. My question is, once you've done your analysis, did you take randomly one of the cases you didn't choose to see if it fits with your methodology and your result?
That's an excellent question, and that's something that I've been wanting to do, and I have not done it yet because we have probably an equal number of cases that we've eliminated. In other words, they didn't quite make the cut, but it's possible some of those could still be valid cases. So I do want to go back and now compare them against the 301.
Okay. Once you've done that, I'll be happy to know what the results. If it's your methodology fits almost perfectly to the other cases.
All of us will be, but I see that there is, I don't know if it is a question by your co-author, Sarah, that has
Yes.
raised hand.
Hi, just a couple comments to the previous question. One of the things that we would like to do for the next paper is to take samples of the 100,000 and compare the distributions of take random samples from the 100,000 cases and compare the distributions of the characteristics that we saw. Of course, you'd have to have samples that had that enough information in them. So we have limit. And the other thing about Edoardo, you were saying, I think that you asked whether Robert had himself done and his cohorts done the selection, but because Robert started, the group started with only cases that had been either curated or investigated, there's sort of an implicit selection that somebody decided that case was worth pursuing because it had enough information. And I think at MUFON, Robert, you can correct me if I'm wrong, but the 10% that are investigated, I mean, somebody's looking at each case and saying that's not worth it, that's not worth it, and then maybe finds one that's worth it. So there is already, somebody has made a selection.
Yeah, that's correct.
Right.
I see Baptiste hand moving on the right of the screen.
Yes, yes, always on the right. Listening to your presentation a second time, because we recorded together, made me think of a saying by Lou Elizondo, who often said that shapes equal functions in UFOs. And I was wondering if you looked into your data for the smallest size possible of a disk, for example, and the largest size possible for a disk, to see if among the different shapes, you could have a typical scale where you would need another technology, so another design, so another shape, to have such a range of motions and craft.
I don't know, Sarah, do you want to answer that one?
I mean, I think we haven't really looked at how the shape that we have would affect possible propulsion, or packaging.
That's my question is just, what is the smallest size possible for a disk? What is the largest size possible for a disk? And same for triangles and spheres.
That would be a lot of conjecture.
Yeah, so you'd look at, I guess Robert was trying to find this size range because the smallest and largest would each be a single report. He was trying to always have at least 3 reports for any particular characteristic he was going to make a statement about. But you could definitely put a size range in there. That would, it wouldn't hurt to include that as information. I had one more thing I wanted to. Oh, sorry, Robert, if you want to say. One more thing I wanted to say about sound. I'm actually working in the acoustics group in the Galileo project, and 50% ish of UAP reports report the unexpected absence of sound. So when you go look at a UAP report, if there is nothing said about sound, that is different from somebody saying there was no sound, right? So you can't just divide your reports into this doesn't have sound, these do. You have actually two categories of no sound. One is nobody said anything about sound, and the other is somebody said, that's really strange, there was no sound. And 50% of reports say, that's really strange, there was no sound. So that's an important little nuance about that sound in reports.
Yeah, great point.
Geoffrey, your hand is still raised. Is that right?
Yes, because I have another question. When you, Robert, when you mentioned the oval shape, did you mean the famous tic-tac shape, or is it another one?
No, it's not the tic-tac shape. We actually had tic-tacs in the database. I think this is from memory. I think we had maybe 3 or 4 tic-tac shapes out of 301, but the oval's a different shape. It's more like an egg shape.
Ah, okay. Thank you.
Thank you, Robert, for this excellent presentation. We really enjoyed, all this analysis and based on the database, on the shape, and that's very very useful to know that it's existing. Thank you.
Yes, I just to say one thing. Look, I think it would be great if someone did that same thing actually just to European reports, right? And then compare them to our paper and see, for any correlation.